Today's discussion is split into two parts. Part one I've already uploaded to YouTube, YouTube channel, and I put the link in the modules section under this week's module, week 5. And the second part I will give here live, and then I will also upload the recording. The first part is about the Root Locus method, and this part is about the Routh-Hurwitz criterion. So for the first problem we have today, we would like to determine the range of values of K for instability of this plant. Okay, see that K appears at the final position in the transfer function, or as the free term in the transfer function. And we want to find the values of K for which the system is unstable. Recall that the stability is characterized by the denominator, right? The denominator polynomial, and we use Hurwitz criterion to judge whether or not the polynomial is stable or unstable. So we construct Routh-Hurwitz as usual. We list the powers of S on the first column, and then we list the coefficients as we go on. So the coefficient for S1, the coefficient for S to the power 4 is 1. Coefficient of S to the power 3 is 1. Then we put here S, the coefficient of S to the power 2, and here S to the power 1. Then here S to the power 0, and then we put a 0 here. And then we continue to construct the Routh-Hurwitz table. A is going to be equal to 1 times 1 minus 1 times 1, right? So we see that A is going to be equal to 0, right? So this, we know already that this is one of the special cases. To find out whether it's the special, the first special case where we use the auxiliary polynomial, or the second special case where we use the epsilon, we need to compute B. So B is 1 times K minus 1 times 0 is going to be equal to K, right? So this means that because K is non-zero, this means that this is the second special case, right? We have to use the epsilon method. So we assume that A is going to be equal to epsilon. Then we continue to fill in the table. C is going to be equal to A times 1 minus 1 times B, right? So that's going to be equal to A minus B divided by A. We substitute with A equal to epsilon and B equal to K. We get that C is going to be equal to 1 minus K divided by epsilon. Then we compute D. It's going to be equal to C times B minus A times 0 divided by C. So that's just going to be equal to B, which is equal to K. So now that we have constructed the table, we look at what happens if epsilon is positive and what happens if epsilon is negative. If epsilon, so A is equal to epsilon, right? So if epsilon is negative, we already get a sign change here, right? Because this is positive, so this will be negative. So if epsilon is negative, which means that its negative is positive, we get a sign change, right? Even without this intermediate step. So we get a sign switch here. However, if epsilon is positive, then this is positive, right? And So we need that C and D, both of them have to be positive, right? So we need that 1 minus k divided by epsilon is positive, and k also positive, okay? So k is positive already dictates that this term is going to be negative, right? Because k is positive and epsilon is positive, and we have a negative sign. Moreover, because we take the limit as epsilon goes to 0, we see that this term, c, will go to negative infinity. So we will get a sign change, right? Because a is positive because it's equal to epsilon. D is positive because it's k. But c will go to, or c will be negative, right? For small values of epsilon. This means that independently from k, we have a sign switch, right? So the plant is unstable for all values of k. Because assume that k is negative, right? If we assume that k is negative so that we can make this term positive, what happens is that this will be positive, and then this will be negative, which will we get a sign change, right? But if k is positive, which makes this term positive, then again, we get a negative term here. So the contradiction between these two terms ensures that for any value of k, we have an unstable system. Any questions? Okay, moving on. The second question we have today is that we would like to determine the range of values of k, again, for stability, this time for the stability of this plant, okay? Again, whenever we try to answer questions about stability, we use the Routh-Hurwitz table. So we list the powers of S as the first column, and then we fill in the Routh-Hurwitz table. It's pretty straightforward to see or to list the coefficients. So we just fill in the table. So I'll just go over filling the table. So A is going to be equal to 3 times 3 minus 1 times 2 divided by 3. So that's just going to be equal to 7 over 3. B is equal to 3 times k minus 0, 1 times 0 divided by 3. So that is just going to be equal to k. C is equal to a times 2 minus 3 times b, right? So that's 2a minus 3b divided by a, right? So we just, after you do the computation, that will give you 2 minus 9 over 7 times k. And then finally, d is going to be equal to c times b divided minus a times 0, which is 0 divided by c. So that's just going to be equal to b, which is equal to k. So for stability, we require that no sign changes happen in the first column, which means because this is positive, we computed a to be 7 over 3, which is positive. So now we need that c be positive and d be positive, right? So C gives us this term, right? Just after manipulating this a little bit, will give us this term that k has to be less than 14 divided by 9. And D gives us that k has to be bigger than 0. So to satisfy stability, or the range of stability, is that k is between 0 and 14 over 9. Any questions? Okay. So the third problem we have for today is a little bit more involved, so I will require your attention. We have a pendulum that is and so this is the case of the inverted pendulum, okay? And recall that the equations of motion of this pendulum are given by this equation of motion, where tau, this tau is the torque applied at the joint around which the pendulum rotates. So this is the case of the pendulum where we can actuate an inverted pendulum where we have some actuation at this joint here, okay? Any intuition or ideas where what might this model in real life? There is a very famous system in real life which we can model by an inverted pendulum.
Isn't it like the motion of walking?
It is, yes, that's one thing. That's definitely motion of walking can be modeled as an inverted pendulum. What else? Think of something recent that happened, like maybe yesterday or before, I don't recall. It has to do with SpaceX. Rocket, basically, right? So a rocket during landing can be thought of like when we do, so let's see. So let's say we have a rocket. Something like this. So the thrust at here, right, gives you, basically you want to counter the weight, right? So you have the weight, something like this. So to get a constant descent rate, you have to counter the weight, but at the same time, you want to balance this rocket, right? So that it lands vertically. So basically, it's like you're trying to balance an inverted pendulum, and that's why it's a very hard problem. So this couple creates a torque that we can think of as this torque that is hinged, or that is activated at the hinge of the pendulum. Have you seen the crash that happened recently? I think it was maybe yesterday or something. So this is a so recall that the equations of motion of this system are given by this equation of motion. Again, T tau is the torque applied to the joint. And for simplicity, let's just say that M is equal to L square is equal to M times L square is equal to C is equal to MLG, just so that we have all the coefficients here equal to 1. Okay. And we basically want to control the pendulum. Okay, we want to control this pendulum. So this is using a simple gain feedback K. Okay, as shown in this block diagram, G represents the transfer function of the pendulum, and K is the gain that we would like to determine its value in order to have stability and achieve something else, okay? So the first part we want to do is basically to linearize the equation of motion, okay, around theta equal to 0 and theta dot equal to 0, which is basically the upright position. And we would like to determine the transfer function of this linearization. So let me erase this. I'll come back to it later. So we said that theta dot is equal to omega, okay? And we say that omega dot, which is going to be equal to theta double dot, we bring it from this, from the equation of motion, right? So it's going to be equal to negative theta dot, which is negative omega, plus sine theta, okay, plus tau. Tau is the torque, okay. Then we linearize this around the equilibrium position, or the upright equilibrium position, theta 0 and theta dot is equal to 0. So that happens basically using the Jacobian, right? So let's call this whole matrix, or this vector, let's call f, okay? So this matrix is the Jacobian of f, right? This is just partial f by partial x, where x is your coordinates like theta and omega. So partial omega by partial theta, that's just equal to 0. Then partial omega by partial omega, that's omega. Then partial this by partial theta is going to be equal to cosine theta. Cosine theta at theta equal to 0 is just equal to 1, right? And then partial this by partial omega is equal to -1. So this is the first matrix, partial f by partial x. Now, recall that we have a torque here, right? And this torque is our input. So if we don't write this term, now I'll say now what this, where this term comes from, we will not have an input, right? So we will not be able to control this, the transfer function that comes out of this. But because we have an input, we basically, the input basically, or this vector is basically partial f by partial tau, where tau is your input, okay? So partial omega by partial tau, that's just going to be equal to 0. Then partial this by partial tau is going to be equal to 1. And that multiplies tau. Okay. Any questions? Okay. So now we go back to the second order differential equation, or the linearized second order differential equation. So theta dot is equal to omega, and omega dot, which is equal to theta double dot, is equal to negative theta dot plus theta plus tau, which means that we get theta double dot plus theta dot minus theta is equal to tau. So this is a second order linear differential equation, right? Which means that we can take the Laplace transform of it. We could not have done this to this non-linear function because of, or non-linear differential equation because of this non-linear term, right? Remember that Laplace's transform works with linear differential equation, linear time invariant differential equations. So going back here, we have that s. So we take the Laplace transform of both sides, right? So we get s squared times theta of s plus s times theta minus theta of s. All of this is equal to t of s, which is just the Laplace transform of tau. So if we look for that transfer function, it's just going to be equal to theta divided by tau, right? So from this equation, we see that g of s is just going to be equal to 1 divided by s squared plus s minus 1. Any questions? Okay, so now we have g of s, which is the transfer function of our system. We would like to find the range of k for stability, okay, of the closed loop system, okay, when we close the loop on this using the value k. We want to find the values of k so that we have stability, and at the same time to achieve a steady state error due to step input that is less than 0.1. Okay. So the solution, first we write the closed loop transfer function, which is k times g of s divided by 1 plus k times g of s, right? which is also the same, is equal to k times n of s divided by d of s plus k times n of s. And d of s is the denominator of the transfer function g, and k and n of s is its numerator, right? So if you do that, you get that it's going to be equal to k divided by s squared plus s minus 1 plus k. For stability, what do you think we should do? What's the tool that we use to assess stability?
Routh, Hurwitz, Criterion.
Yeah, exactly. So again, we constructed Routh Hurwitz table. So this is a second order polynomial, which is pretty easy, right? So we need s squared plus, so we have s squared, s to the power 1 and s to the power 0. We have the coefficients 1, k minus 1, and 1. So we compute this term here, which is basically k minus 1 times 1 minus 0 divided by 1, so which is going to be equal to k minus 1. So clearly for stability, we need that no sign changes happen here. So we need that k has to be bigger than 1. So this is the requirement for stability, right? Now for steady state error, we need to use the final value theorem, right? So ESS, which is the steady state error, is going to be equal to the limit as s goes to infinity of s times e of s, right? Which I'll let you do the details, but you can see that it's going to be equal to 1 divided by k minus 1, which implies that we want the absolute value of that to be less than 0.1. Okay, it's important to keep in mind here that we're looking for the absolute value. So the absolute value implies that bigger, and then we get two solutions, either that k is bigger than or equal to 11, or that k is less than or equal to -9, right? But we already found that for stability, we need that k has to be bigger than 1, right? So we already know that we are going to reject the k less than -9 because for two reasons. First of all, the system will not be stable. The second reason is that because the system is unstable, the final value theorem is no longer applicable, and whatever comes out is already garbage, right? So this, we have to reject this, the solution to this inequality. And so to achieve both goals, we see that the range k has to be bigger than 11, right? Okay, any questions? Okay, this was pretty straightforward so far. This next one will be a little bit tricky, so I need you to focus. Now, suppose that there is some delay, okay, of delay in the controller implementation of 2 times epsilon bigger than 0, okay? This is delay in the controller implementation, and epsilon is assumed to be small, okay? We want to find an approximate value for the maximum allowable epsilon before instability. Okay, and we're going to assume that k is equal to 11. And having a delay in a control loop is a very typical situation in control systems. So the plant is a physical plant, right? Meaning it's basically the pendulum or a rocket or whatever, right? This is just the dynamics, and this is real time. Like what happens now, this does not have any delay, right? This is just a physical system. However, because we are using a digital computer, right? And we are basically measuring. So this is the sensor, right? This is the sensor loop. So to do the feedback, they're basically using the value or measuring first, right? Theta, what theta is. And then we are applying a controller, right? So there might be some delay in the computation here, or due to sensing or whatever, like anywhere along this line here, there might be some delay in the system, meaning that the value that you're computing right now used a measurement that happened a few milliseconds ago, right? So we want to model what happens exactly when we add a delay to a system, okay? We want to find how much delay we can tolerate in the system without hitting the boundary of stability, without basically the system being unstable. That's the goal of this exercise. So the delay is modeled by a transfer function by this exponential here. So d of s equal to e to the power -2 times epsilon times s. This is the differential equation. Oh, sorry, this is the this is the equation that models the delay in a transfer function setting. And we can easily see that if we have a delay f2 epsilon, we can just write this as e to the power negative epsilon times s divided by e to the power epsilon times s. Okay, so far everything is exact. We didn't do anything. Now because we want to compute an approximate value, okay, what we do is that we do the trick of Taylor expansion. So we expand the numerator, okay, into a Taylor expansion. And also the denominator, we expand it as a Taylor expansion, okay? And we basically truncate this Taylor expansion after the first term. So we neglect these two tails of the Taylor expansion as a first order approximation. And we see that for small values of epsilon, like when epsilon is on the order of 0.01, we see that this Taylor expansion is actually pretty accurate in modeling the delay introduced in the system. So we try to approximate the delay by basically adding a right half plane 0 and a left half plane pole, right? Because epsilon is positive, so this is a right half plane pole, right half plane 0, and this is a left half plane pole. And now the system becomes, we add the delay here. We assume that the delay is between the controller, which is the computer, okay, and the actual plant, okay. So we just combine D and G together. We call it GD, okay. And so GD is just going to be equal to the multiplication of G with D, right? So we get the 0 and 3 poles. Any questions? Should be straightforward so far, right? Okay. We proceed to compute the closed loop transfer function after we have added this delay. So the closed loop is basically, again, going to be equal to k times jd divided by 1 plus k times gd. When you do the computation, you will find out that t of s is going to be equal to this expression. Notice that we have epsilon, okay, and in the numerator we have the 0 at 1 minus epsilon times s. Again, for stability, we have the Routh-Hurwitz criterion. So we proceed to construct the Routh-Hurwitz table. This is a third order polynomial, right? So we start from that. S to the power 3, S to the power 2, S to the power 1, and S to the power 0. Then we list the coefficients, epsilon, 1 minus 12 epsilon, 1 plus epsilon, and 10. We compute A and B. So A is equal to 1 plus epsilon times 1 minus 12 epsilon minus 10 epsilon divided by 1 plus epsilon, which is this here. Okay, when we carry out the multiplication, we will get a quadratic polynomial in the numerator for epsilon, and we will get 1 plus epsilon in the denominator. Okay, so this is B, so this is A. Now we compute B, which is equal to A times 10 minus 1 plus epsilon times 0 divided by A, right, which is this computation here. This term cancels, and the A cancels with the A. So we get that B is just going to be equal to 10. So for stability, we require that no sign changes happen in the first column. So epsilon is positive, right? And this is positive, and this is 10, which is positive. So we require that A has to be bigger than or equal to 0 so that we have stability. Okay. Any questions?
Yeah. For the next steps, do you have, so A is greater than or equal to 0. For the rest of the steps, does it matter if it's greater than or equal to 0, or is it just greater than?
So whenever you have something like this, the value that happens, or the values for epsilon that happen to exactly be equal to 0, these are critical values. Like you typically want to go away from those. Because like if A is equal to 0, you have a row of zeros, right? So you have to do the auxiliary polynomial kind of thing. Does that make sense?
Okay.
Yeah. So typically critical values like I'm not gonna so how to put this? Like if you do the auxiliary polynomial and you happen to have no like if you do the auxiliary, because if A is equal to 0, you'll get a 0 here, right? Then if you happen to do the auxiliary polynomial and you find out that you have no repeated poles, then the system might be marginally stable. Like if you have a situation like this, the best you can hope is marginal stability, which is still not a very good form of stability, right?
Okay.
Okay. Any other questions? Okay. So going back for stability, we need that A has to be bigger than or equal to 0. So this is the expression for A. Again, I'm not paying a lot of attention here. Let's just put, or let's, okay, so let's just drop this equal sign. It doesn't make a big difference. So yeah, so we want that A has to be bigger than this, right? Which, well, again, because epsilon is positive, so 1 plus epsilon is positive, we can multiply both sides by 1 plus epsilon to get that this must be true. 1 minus 21 times epsilon minus 12 epsilon squared has to be positive. If we multiply both sides by negative 1 over 12, we get this expression, and notice that we reversed the sign, the direction of the inequality. Okay, so this is a second order factor, a second order polynomial. We can factor it out into two factors, right? Epsilon minus epsilon 1 and epsilon minus epsilon 2, where epsilon 1 and epsilon 2 can be found by the quadratic formula, because we have 7 over 4 and 1 over 12, right? And so we compute that epsilon, we can actually compute that epsilon1 is going to be equal to approximately negative 1.8, and epsilon2 is going to be equal to 0.045. So we want to find the range of values for epsilon such that this factor is negative, okay? So this multiplication is negative. So we have two factors. Let's look at the signs of both of them and see what happens when we multiply them. So the first factor, which is epsilon minus epsilon1, is positive when epsilon is bigger than epsilon1 and negative when epsilon is less than epsilon1. Similarly, the second factor is positive when epsilon is bigger than epsilon2 and negative when epsilon is less than epsilon2. So when you multiply both factors, a positive times positive, right? That will be positive. Okay. And negative times negative, that will be positive again, right? And so when epsilon is bigger than epsilon2, or if it's less than epsilon1, we have that the multiplication of the two factors is positive. So we drop that range. We see that it only, or this multiplication is negative only when epsilon is between epsilon1 and epsilon2, right? Because we will have positive multiplying negative will be positive. Yeah, will be negative, sorry, right? And so this inequality, oh, this inequality is satisfied when epsilon is between epsilon1 and epsilon2, which is negative 1.8 and 0.045. However, from stability, we already require that epsilon has to be positive, right? And we also know that in the problem statement that epsilon is positive. And so we just need that epsilon be bigger than 0, or epsilon bigger than 0 and less than 0.045. Okay, so the maximum value for epsilon that can be achieved is approximately 0.045. Which implies, because the actual delay is 2 times this value of epsilon, the maximum allowable delay we can have is 0.009 seconds. Okay, so this is the maximum delay that we can allow for this system. Any questions? Okay. Finally, let's put epsilon equal to 0.04, okay, seconds. And let's try to sketch the root locus of the plant using MATLAB, okay? And for that particular value of epsilon, let's try to determine the gain at which we have j omega crossing from the sketch. So what does, can anyone tell me what does j omega signify, the crossing of j omega signify? Any ideas? What happens when the root locus crosses j omega axis, which is the imaginary axis?
It changes stability.
Yeah, exactly. It changes from, it becomes marginally stable at the exact value where it crosses the imaginary axis, and then it goes to instability, right? If we try to increase the gain k any further. So let's go to MATLAB. So let's continue. We start by setting s equal to tf of s. Then we put our transfer function, which is g equal to 1 over s squared plus s minus 1. And then we put the delay epsilon is just going to be equal to 0.04. Then we put the delay transfer function, let's call it d, and it's equal to 1 minus e times s divided by 1 plus e times s. Okay. And then we create a function gt, right, which is basically d times g. And we want to have a look at the root locus of gt. Okay, so you see this is the root locus. Let's try to zoom on this section here. So we have this 0, right? This is the right half plane 0 for the delay, and this is the left half plane 0 for the delay. And we have these two poles of the original system. Because of the presence of this 0 and this pole, we see that, actually let me show you, so subplot 2, 1, 1. 2, 1, 2. Okay, so without this 0 and this pole, we see that the root, the root on the right half plane will just move towards the pole in the left half plane, and then they will meet here at point negative half, and then they will just go vertically. Both of them will go vertically to infinity. Okay, but because of the presence of this 0, okay, one of the poles will go to they will, because of the presence of this 0 on the right half plane, they will move towards this 0. Okay, and then they will meet again. And then one of them will break off to positive infinity, and the other will go to the 0 here. Okay, and so the presence of this 0 affects the root locus by pulling it to the right half plane, which introduces this stability, instability, right? And that happens at some gain, and we would like to find the gain, right? The gain in which this crossing happens. So if we look at this root locus, we see that the gain, or the crossing happens approximately over here, right? Which is about at a gain of approximately 13 point something. So we want to, if we want to refine this portion a little bit, we can do that by specifying the values of the gain. So we put linspace starting from 0 up to, let's say, 20, and we get a step of 1e to the power 4. And we give here k and k. So we see, let's try to zoom a little bit here again. And look at this point. We see that the gain at which we get a j omega crossing is approximately 12.7. Okay. Now let's try to increase that delay a little bit, or not a little bit. Let's make it 0.08. Okay. Now, because epsilon because the delay, the actual delay in the system we know is 2 times epsilon, right? So we are simulating the effect of adding a delay of 0.16 seconds, okay? Let's see what happens when we increase that delay. Root Locus pretty much did not change a lot, right? But if we zoom a little bit here, we see that the value, that now the current value at which the system crosses the imaginary axis is much less, right? It is 6.45, which is much less than the value that we had before, approximately half of that, right? So increasing the delay in a system significantly limits the controller that you can implement, right? Because now we see that the maximum gain we can achieve is 6.45, and if you try to simulate the system at this gain, let's say 6.45, we see that the steady state error will be significantly higher than the required value, which is 0.1, right? So let's compute TE. T equal to feedback of GD, or so this is, say, 6.4 times GD, or times G, and 1. Okay, then let's have a look at the step of that. Step 1 minus T, just to look at the steady state error. Okay. Let me comment this for a minute and run this. We see that the steady state error is 0.19, something like that, right? Like if we look at characteristics, the steady state, we'll see that the steady state is negative 0.185, which is like 8.5% higher than what we want, right? Also, if we try to compute the closed loop system for the transfer function with the delay, 1 minus TD, we will see a significant amount of oscillations, right? Because of this delay. Like the original system is, which is in blue, right? Somewhere here. It's much more stable. Like you don't get this amount of oscillations. And even though both of them have the same steady state, both of them go to, both steady state errors go to 18.5, like 18.5%. The steady state error for the system with the delay has a lot more oscillations, right? Because exactly of that delay. And it takes a much longer for the system to settle down. So the conclusion, what I'm trying to say here is that delay really is a very bad thing to have in your controller. Like if you have a delay, even if it's a very small amount, like we can put 0.1 here, for instance. Okay, let's try to simulate this. You still get these weird oscillations, right? It takes longer for your system to settle down, even though that the steady state is not affected. Let's try to increase it a little bit, like 0.2. You see that the oscillations grow larger, right? We try to increase it to 0.4. Oscillations keep growing, right? And that's particularly because of the form of the delay. It's because of the delay appears as an exponential term, right? And so the increases here are not proportionate. Like if you go to 0.6, we are getting closer and closer to the boundary of the instability, right? We see again, the oscillations are growing further and further. We should do 0.7. You can see we are right now, we are getting very close to the boundary of instability of the system. And so things can become exceedingly oscillatory, and you will get a very bad behavior. So that concludes my present. I think there's one last thing I want to discuss. So remember that we did a first order Taylor approximation, right? We can enhance this Taylor approximation by including a higher order term, which is basically e to the power 2, right? Or e times e divided by 2 times s squared, okay? And similarly here. Right, so this means that we took a second order Taylor approximation, right? And we neglected anything of a third order or higher. Let's see what happens to, so let's comment this and comment this. So recall that we found the value for the gain here for when e is equal to 0.04. We found that the gain was approximately, or the gain, the G omega crossing happens approximately at 6.45. Now let's see what happens when we add this higher order term. We zoom again a little bit over this section. And we look at the crossing. First, you can clearly see that the root locus has now a different shape because of the additional. So taking a higher order term adds 2 zeros instead of 1 0, and 2 poles instead of 1 pole. So we focus on this portion, and let's look at gain here. We see that the gain is now 6.37, whereas previously we found it to be 6.45, right? But actually it's like something like 6.3 something. So we see that the more, like if we try to include third order terms and so on, this the difference in the gain is not that large. So we see that for small epsilons, when the delay is already small, the approximation by first order Taylor expansion is actually pretty accurate and gives you some margin of stability that you can work around, and it's also pretty simple to deal with, right? Because just we add like 1 0 and 1 pole, whereas for higher order Taylor expansions, the root locus will look more complicated because we will have different behavior. Okay, that concludes my presentation, my discussion today. Any questions? Okay, well, thank you guys, and good luck.
Thank you. Take care.
You too.